Okay, so we have finally come to one of our big theorems that tells us something very special about conservative vector fields. So let's suppose that we have a region in the plane or in space, and our function phi is a differentiable potential function defined in our region. And let's also suppose that f is the gradient of phi, and f is a vector field. Which means that f is a conservative vector field because it's a gradient. That's by definition must be conservative. That means we can find its potential function, as we've done in the last few previous examples. Then we have the following result. And I'll try to explain what it means, and then we'll do a quick proof of it. But this is the fundamental theorem. It says the following. The line integral over the curve of our vector field. So recall that this means our integral, our circulation integral that we measure by figuring out how much of the vector field points in the direction of the curve, of the tangent. And our theorem says, okay, no matter what curve I have here, we can just evaluate this by evaluating the potential function at B minus the potential function at A for points A and B in our region R, and C is a smooth oriented curve, from A to B. Okay, what does this mean? This means, look, it doesn't really matter what my curve is, because this is telling me that I can measure the circulation of my vector field over any curve, and it will be the same. If I start at A and end up at B, it's going to be the difference between those values. So for example, if I take, I'm going to pick a green color, and I have a curve in my diagram from A that goes to B, and I'm able to measure the vector line integral of the circulation vector line integral for that curve. And I get some value. And I pick another curve from the same starting point to the same ending point, and I'm going to get the same value because these two curves are going to, it's the vector field has a potential function phi, and all I have to do is evaluate phi at the endpoints. So no matter what curve I pick, maybe I'll go something like this. If I start and end at the same 2 points, then we can calculate the vector line integral, and that will be the same. And this also implies that we actually have independence of path. So I'll write that definition down now, and then we'll prove this fundamental theorem. So you can see here that we really have independence of path. Let's think about what this means. So if we have, in fact, this special kind of vector field, so F is a conservative vector field, then the value of the line integral of F, which means our circulation integral, depends only on the endpoints of our path. So if we have a conservative vector field, I can take whatever path I want from point A to point B, and I'm going to do the same amount of work no matter what path I take. That's what that means. So the gravitational field actually is conservative, which means that if you move an object from point A to point B, no matter what path you take between them, if you end up at B and you started at A, you're going to do the same amount of work. And the gravitational field is going to do the same amount of work on that object and moving that object. So let's do a quick proof of this theorem. So I'm proving the fundamental theorem of line integrals. And before I prove it, let's just recall the chain rule, the following form of the chain rule. So this form of the chain rule tells us that if I'm differentiating a composition f of r of t with respect to t, we take the partial of f with respect to x and multiply by dx dt, and add to that the partial of f with respect to y and multiply by dy dt. Here, I'm thinking of r of t as a vector function with components x and y, which are functions of t. Let me write that a little more clearly, which are functions of t. So x of t, y of t. So just a reminder of the chain rule, because we're going to see a form of it in this proof. All right, so let's write down our vector line integral c of f dot dr. Now, if f is a conservative field, that means that I can actually write this as the gradient of phi dot dr. And, well, okay, so that's the same thing as writing integral from a to b of the partial of phi, gradient of phi, dotted with r prime of t dt. And, well, you can see that this dot product of a partial of a function and r prime, right? Here's r prime, dx dt, dy dt, that's r prime. df dx, df dy, that's the gradient of some function f, or in this case phi. So I can rewrite this as the derivative with respect to t of phi of r of t by the chain rule dt. Right, so here's where I'm using the chain rule. The derivative with respect to t of this thing is in fact d phi dx times dx dt plus d phi dy times dy dt. And that's exactly this dot product. And so that's the derivative of the composition. Now, by the regular fundamental theorem of calculus, so by our regular FTC, we know that the integral of this derivative is going to be phi of r of t from a to b. That's what the fundamental theorem of calculus says from calculus 2. And that's going to give us phi of r of b minus phi of r of a. So that's the same thing as saying phi at point b minus phi at point a on our curve. And so we have proven the fundamental theorem of line integrals, and it just relies on the fundamental theorem of calculus and the use of the chain rule, understanding that what we have here is actually the derivative of this composition. And when we write it as that, then when we integrate the derivative of a composition, we get the function itself by the fundamental theorem of calculus, and then we have our result from the fundamental theorem for line integrals. So once again, this theorem tells us that, oops, I didn't mean to move that. This theorem tells us that we have independence of path if we have a conservative vector field. In other words, the value of the line integral over a conservative vector field only depends on the endpoints of my path. It doesn't depend on the path that we take.